Good morning and welcome to AXA XL Arctic Live. We are here in the high Arctic on the island of Svalbard, and we're based at the UK Arctic Research Station in the International Science Village of Ny-Ålesund. And it's great to have you all with us. We have schools from India and the UAE watching this morning. Wonderful to have you with us, because what we're doing today is we're going to look at ocean acidification in the Arctic. Now, the research team has just gone out in the boat to collect some water samples to see how the ocean chemistry is changing, and in particular looking at pH. My name's Jamie, and I'm going to be working with you today through a number of sessions, and we're going to be looking at different things. This morning in the first session, we are doing a live investigation. So we're going to be looking at the basics of ocean acidification, the process that occurs there. In a couple of hours' time, we're going to have Hannah Green join us, and she is a PhD student in polar oceanography, and she's part of the research team here looking at ocean acidification in the high Arctic. We'll talk through with her career so far, some of the science behind ocean acidification, and maybe some of the things that we can all do to learn how to mitigate the impacts it's having on life up here in the Arctic. We'll then have an Arctic Q&A with myself and Ellie, who's currently behind the camera, and then for our North American audiences, we'll do the live investigation and expert interview again. So this live broadcast based around a live investigation, but we'll do a few other things as well. We're up here in this wonderful place, Ny-Ålesund, the northernmost permanent community in the world, and we'll go outside in just a bit and have a look around and show you what this amazing but fragile ecosystem is like. And then we'll show you a little bit of the research station, and then come back in and do a couple of little investigations. Really, the science skills we're looking at in this session, we're looking at predictions and we're looking at observation. So those are a couple of things we'll be focusing on. And then at the end of this session, we will have time for a little bit of a Q&A, just to go through any questions you might have, whether it's about ocean acidification or whether it's about life and science in the Arctic. Can be quite general. This is my 8th polar trip. So if there are any general questions you have about the polar regions, especially what it's like to be up here, do get those ready for later in the broadcast. So without further ado, Ellie, are we ready to have a little look outside? It's a lovely warm day today. I think it's about -2, -3, and the wind hopefully is not too big, because if we've got a big wind, a strong wind, then it means we've got big waves out in the fjord, and the science team will have a very bumpy time. Someone's locked the door, have they? Not very good for polar bear. So one of the interesting, it's not good for polar bears. What I meant to say was that traditionally up here, that you will keep your doors unlocked. So if you're walking around as a polar bear suddenly comes around the corner, you can dash into any building without having to worry about whether the door is locked or not. As you can hear behind me, the wind is up a bit, and I wouldn't be surprised if we saw a couple of scientists coming back. The last sampling site we have is way out towards the open sea, and we had a very calm day yesterday. We had a good chop of about a meter and a half. Very difficult. The conditions were so bad that in fact we ripped through one of our sampling nets, completely shredded by the Arctic Ocean. And while it can be a beautiful place to work, it is also an incredibly difficult place to work. So I'm just going to turn around if I can, and hopefully won't be able to shelter the microphone. But the view out here, I think it's one of the most spectacular views in the world. It's very difficult to estimate the distances. So at the head of the fjord, and the fjord is the name we give to the sea inlet running alongside the research station, coming from the Fram Straits, where the sort of Atlantic and Arctic Ocean meet, which is sort of down behind us. you can see the glaciers, and I think that's the Chronobrain, the big sort of crackly glacier out there. That's about sort of 10-15 kilometers away, about sort of 8 miles away, just to give you a sense of distance. And the peaks behind those pyramidal peaks, those are another 10-15 kilometers away. So that's about 20 miles to the back of those mountains in the distance there. But the air is so clear up here that you can see those, and it seems like they're sort of just about in touching distance. It's also sort of little reindeer mooching around on the shoreline there. Not quite sure whether we can pick that up on the camera. But it is a stunning place. But the wind's up, and I imagine people's fingers will start going. Ellie, I know that we thought it's a warm day. You don't have gloves off, and you're holding metal up. So we'll just quickly sort of look at the research station here. So we're not sleeping in tents. I have slept in tents out on the sea ice, but we're in a research station. What this means is that we have bedrooms, we have lab space, we have office space where we can all be quite comfortable. Then we'll be walking down this road, down to the little harbour, getting out onto the boats, and heading off around the fjord to collect our samples. We've been on the inner fjord, which we saw just before, heading to the outer fjord today. The Ollesund is a collection of many different research stations, and we'll just go inside because I can see the sort of, the comfort levels in holding a metal camera up in probably felt a bit like minus 10, 15 degrees Celsius with wind chill. So let's come inside. There are in fact 10 different countries represented in the research community up here in the Ollesund. So really a international science community. And the science community is a wonderful mix between what we call marine, studying the sea, terrestrial, studying the land and the glaciers here, and atmospheric observation. So you get that really great mix of those three disciplines. What we're looking at today is some of the marine science that's being carried out here, and this idea around ocean acidification. Now, before we start, I'm just going to go through what ocean acidification is, just in case it's a new idea or concept for you. We're going to start off with atmospheric carbon dioxide, and maybe some of you are already familiar with the growth in emissions through industrial processes, the combustion engine, burning of fossil fuels. And so when we burn a fossil fuel such as oil, gas or coal, part of that we release into the atmosphere carbon dioxide. Now 30% of that carbon dioxide is absorbed into the ocean. So that carbon dioxide, increased levels in the atmosphere, then absorbed into the ocean. And when it's in the ocean, it undergoes a chemical process, a change, and that goes from carbon dioxide dissolved in the water into carbonic acid. Now, carbonic acid is a weak acid, but it changes the chemistry, it changes the pH of the ocean. So what we're looking at is that the acidity of the ocean has increased by 30% since the Industrial Revolution, so since the 1750s. So in the past 250 years, the acidity of the ocean has changed by 30%. Now, that may sound like it's taken a long time, but that is the fastest changes in the past 300 million years. So we're undergoing an incredibly rapid change in ocean chemistry at the moment, and it's happening in the Arctic fastest. Now, the couple of reasons why it's happening up here faster, but the one that we probably have observed in our own daily lives is that cold water absorbs gas better than warm water. And I'll tell you where you might have encountered that, and that's with a can of fizzy pop. So if you have a very cold can and you open it up, it doesn't spray everywhere. If you have a warmer can, it can spray everywhere, and that's because the gas is no longer being held in solution. So we're going to look at this. We're going to see whether we can replicate that change in ocean pH caused by increased levels of carbon dioxide. And so we're going to do the first of our live investigations. Now there are basically sort of three things that we need. We need a container with some tap water. We need a straw. Please try and cut down on single-use plastic straws. This is a metal one. You can get paper. And a way of measuring the pH. Here I have an electronic pH meter. Other options are available. You can make your own pH indicator dye using red cabbage, or school supplies may give you things like litmus paper, which change colour depending on the pH levels that you are testing. So what I'm going to do now is going to put the pH probe into the water I'm testing. What we're looking at is if I blow through this water, what might happen to the pH. Now, when I exhale, I have increased levels of carbon dioxide in my breath because of respiration. And I'm going to blow that through some water, and I'm going to see how the pH level changes. Now, what I want you to think about in your class at the moment is how might the pH of this water change if I bubble carbon dioxide through it. So think about what you consider will happen, a prediction, and then we'll test that to see if that comes true. When you are blowing, don't blow too fast because you'll basically spill the water everywhere, and don't blow for too long because you may pass out basically. So take it in turns. Use a straw, one per student, just for hygiene purposes, and maybe take it in turns for 15 seconds. We're going to do this for 2 minutes, and I think hopefully Ellie will be able to time me through that. And what we're going to do is we're going to see if the pH changes. Ellie, I'm just going to hold up the pH meter. Ooh, don't want to knock that solution over. Wires everywhere. So at the moment we have a pH, I think around, just hovering around 7, about 6.97. 7.02. Oh, 7.02. It's sort of fluctuating a tiny bit. Great. So I'm going to put the probes back in here. And then tell me when I'm ready.
Okay. 3, 2, 1, go. 1 minute. Five, four, three, two, one, and
Okay, there we go. So, put the pH probe back in. See if there's going to be any change at all. So you'll have blown through. There's rather pathetic changes are happening in my my batch. So you will have blown through your water. I have, for some unknown reason, given myself about twice as much water as I've ever done before, and we have seen a slight change in the pH. So I have a pH now of, is that 6.93?
Yep, 6.95.
6.95. So
94.
93.
Yeah.
So that is a 0.1 of a unit change.
Yep.
So that's about a 30% increase in acidity there. I wonder how you've got on at your school. I'm quite tempted. Should we do 2 more minutes to see whether there's a change? I know it makes great live broadcast to watch me bubbling through water, but it also gives you a chance in the classroom to do it yourselves. So I've gone down from 7.02 to 6.93, and I wonder whether we can just start cutting that a bit lower. We'll do. Oh, can I just check, Ellie, the reading on there before I put that down?
6.87.
6.87. Okay. Oh, 6.87. Okay. And we'll see if we can get that down even more. Very lucky I have 30-second breaths. We ready?
Ready? 3, 2, 1, go. 4, 3, 2, 1, and stop.
Okay, so we've gone from 7.02 to 6.87. Bring these probes back over, put them into our breathe through water, and we'll just let the pH meter gently work its way through. Give it a bit of a stir, always good, and we'll let that settle down. What we saw before was it just took about a minute to make that change. So I'm just wondering how you got on with yours and what you predicted as well. So our predictions before were looking at the process. So we have increased levels of carbon dioxide dissolving in the water and becoming a weak acid, carbonic acid. So the more carbon dioxide we put through, the more acidic the water will become, and then we'll see a drop in pH. So it's rather odd, it's the other way around. We have a increase in acidity means a drop in pH. So we're just seeing what's going to happen with this. We have a further drop. We've got 6.79 at the moment. 6.8, 6.79. That
6.77.
6.77. So every 2 minutes of blowing, we're getting about 0.1 of a unit drop.
0.75.
7.5. It's dropping. There we go. It's taking a rather long time to do that. Seven four. Well, let's let that on the side there. If it drops any further, we can have a chat through that. So what we're seeing is roughly 0.1, 0.15 decrease in a unit of pH. So that has become sort of about 60% more acidic over the past 4 minutes. Obviously, that is not the rapid rate that we're experiencing in the ocean. It's been from about 8.2 in 1750 to about 8.1 on average now in the ocean. The predicted changes by the end of the century are a further decrease of about 0.4 of a unit, so down to pH 7.7. And because the pH scale is a logarithmic scale, what that means is that by the end of the century, we'll have experienced an additional 120% increase in acidity. Now, do please send through any of the questions you might have about pH, about ocean acidification, and about life in the Arctic, because we're going to move now to the second part of our live investigation into ocean acidification, and that's looking at its impact on some of the living things. Now, some people refer to ocean acidification as climate change's evil twin, and while we don't have to always use that kind of language, I'm just going to go and grab a couple of things. Actually, we've got down to 6.64. So we have, so if I sit on that one, let's move this to one side. What we're going to look at is some different forms of life and how they might respond to changes in ocean pH. Now, there are a lot of animals out there that have what we call calcium carbonate, so limestone shells or structures. So if we think about clam or shellfish or crustaceans or coral, they have their shells and structures made out of calcium carbonate. Now, calcium carbonate is a mineral, chalk, limestone. So I have the equivalent of calcium carbonate in these sticks of chalk. And if these bits of chalk, these proxies for sea life, go into a more acidic ocean, some changes might occur. So I'm just going to use malt vinegar for this as my acid. I'm going to pour a little bit into here. It's quite smelly, this, so we might have to get some brisk Arctic air through the studio in a little bit. I'm just going to put these in here, and we'll get a close-up, Ellie, and see what we can observe if we put these equivalent of sea life into an acid. We see anything happening here. Can I put it, if I put it backlight it?
No, if you can bring it closer.
Like that?
Yeah.
I can see.
That's good.
Yep.
Yeah.
And the reason why I break up the chalk is quite often sort of modern chalks have a coating on them to prevent the chalk rubbing off on your hands. So it's important, if it's not, you don't see any changes, just to break it up a little bit. So what we can see at the moment is the chalk reacting with the acid and in fact dissolving. We probably won't see that kind of dissolving of vast quantities of marine life. It doesn't mean ocean acidification doesn't mean if you sort of go swimming you are going to have your foot dissolved. What we're finding is that what increased ocean acidification means is that there's less availability of these building blocks, of these calcium carbonate building blocks for life. So there's less of that around, and so they're having to use more energy to build their structures. Sometimes the structures are a bit flimsy, so they're not as good protection from predators. Sometimes they are just using so much energy they don't have that energy left for reproduction and for growth. So we're seeing some smaller examples. And so while ocean acidification might sound like it's an acid ocean and it's going to dissolve all marine life, in fact what we're seeing is it's putting pressure on a number of different types of sea creature, just because building their structures is taking that much more energy. Going into the future, and in fact there are some examples I think already where certain types of more fragile creature are experiencing very translucent and thin structures, but it's not something that we see across the board. And in fact the responses to ocean acidification vary between different types of animal, some benefiting, some not. We will have Hannah in just over an hour with us to go through some of those as well. So what we have done today is we've looked at two investigations into ocean acidification. We've looked at the process, and what we can see is that more carbon dioxide, whether it's into the atmosphere because of burning fossil fuels or breathing through a straw, absorbed and dissolving into the water, is changing its pH. The more carbon dioxide we put into the atmosphere, the more the pH of the ocean will change, with a prediction of a further 120% increase in ocean acidity by the end of the century. What we've also seen is that increased pH. We've observed how the chalk has reacted with the vinegar. The vinegar is much stronger acid than we are predicting to see in the ocean, but what we're seeing is, on a quite sort of exaggerated scale, how this can affect marine life, and especially those animals with carbonate structures or skeletons. And that is putting increased pressure because of the lack of carbonate ions in the ocean, increased pressure, and it means that they have less energy for building their shell. I mean, less energy, having taken more effort to build their shell for things like growth and reproduction. We'll move on now to seeing some of your questions coming through and finding out. Is it okay? So I come back. Yep. With it's very difficult to film in the studio at the moment because we've got the rapidly changing sun angle and 24-hour daylight. So we're just shifting between different seats to make sure I'm not too backlit. But I'm just going to get your questions up. The first question coming through is from the Dubai British School, Jumeirah Park. And how will ocean acidification affect humans? That's a really, really good question. So it's more of an indirect effect. So what we're looking at is how will it affect the ocean ecosystem, the marine ecosystem. And we're seeing that some of the smaller creatures, the zooplankton, so that's things like copepods and amphipods and isopods and all the other pods, are being affected by ocean acidification, either not getting big enough, or we're seeing in very, very exaggerated sort of experiments where copepods and the larvae, the naupliae, are put into the predicted pH for the end of the century. Their survival rates are going down. So they're at the bottom of the food chain. So if you have less or smaller creatures at the bottom of the food chain, there's going to be less availability for fish and for bigger marine animals. And with about 1 trillion people relying on the ocean for their primary source of protein, that's a massive, massive potential impact on fisheries and therefore on people. So that's one effect of ocean acidification on people. The other one, which I think there's still current research going into, is that there are a number of algae that photosynthesize and produce the oxygen that you breathe that make their structure out of chalk. They're called coccolithophores, and looking at how those different species might be affected by ocean acidification as well. So there's potential impacts on oxygen and there are definite impacts on the food chain. There's a very big case a number of years ago and probably ongoing where the oyster fisheries in Washington state on the west coast of the US were very badly affected, and especially the larval stage, and there was a multi-million-dollar funding to support the oyster fisheries there. So we're already seeing the direct impacts of ocean acidification on fisheries. Second question coming through, is there anything we can do to stop ocean acidification? I mean, I'd put this back to you. So we've looked at the process and what the driver is for ocean acidification. So we're seeing that it is increased atmospheric carbon dioxide. So it's really reducing atmospheric carbon dioxide. And we can talk more broadly about how to reduce carbon emissions. I mean, very, very simply, I would take it in 3 stages. The first stage is looking at how you travel. So are you taking lots of planes? Are you driving in cars? How are you traveling? And how can you move to a less carbon intensive form of travel, such as by foot or by bike? And I realise in cities like Dubai, where the infrastructure may not allow for that as easily, it's a more difficult question to answer. We can come on that. Please do put comments onto the live chat. We can start to debate some of those points. The second piece is looking at how you eat. So we know, for instance, if we move towards a plant-based diet, we are dramatically reducing our carbon emissions. Someone said to me that Ferrari driving vegan has a smaller carbon footprint than a barbecue loving bicyclist. So really focusing on your diet is a big way of looking at reducing your carbon footprint. And lastly is looking at how you live, so how much you consume, what you buy, where you get your clothes from, whether you leave the television on all night, the lights on, the types of energy saving pieces you might have at home, where you get your household energy from. Do you have a gas cooker rather than an electric cooker? So all those little pieces in the home environment, looking to help reduce carbon emissions. There have been some ideas around something called geoengineering, and that's where we can suddenly come up with a cunning solution to change the chemistry of the planet by doing things like dropping radical amounts of iron filings into the ocean to try and boost algae growth in the oceans, and that algae will take the carbon dioxide out of the water, seawater. Those I haven't seen anything that shows that it can work at scale, but happy to be proved wrong on that account. On a personal note, I do feel that instead of trying to engineer solutions, maybe we try and live within natural systems. Might be a way in which there will be fewer unintended consequences of our actions. We have, what damage is ocean acidification causing to the Arctic marine environment? That's a really great question. What we're seeing, it's varied. We did an investigation on krill, which are a type of Arctic zooplankton, and we collected them in late April, early May 2014 on the first Arctic Live. And they were living at the head of the fjord and were in fact experiencing quite a wide range of pHs. That is because with the ocean pH of about 8.1, there's also fresh water coming from the glacier at the head of the fjord. So they're experiencing quite a wide mix of pH. And when they're exposed to predicted pHs, acidity levels for the future, their survivability was actually not too badly affected. However, on looking at predicted changes in pH and its impact on copepods in the Canadian Arctic on a research trip in 2011, we saw that there was much higher mortality, especially for those species of zooplankton that didn't experience that big a change, and especially on the larval stages as well. So we saw sort of impact of that. At the moment, I don't have fresh samples from the fjord out here to see if we can identify whether there is any direct impact on the species here, but we'll certainly ask the team when they get back from the fjord if they have spotted that, for instance, the shells of some of these small creatures haven't fully formed as yet. But what we're seeing is a variety of different changes, but especially concern around the larval stage of the plankton up here. This is from Star International Altoir. How does acid affect the water and wildlife? So what we're looking at here is just to disentangle some potential misconceptions. So we're looking at the pH or the acidity level of the water. We're not looking at adding, sort of like getting hydrochloric acid and pouring it into the sea. That's not quite what's happening. So we're looking at how carbon dioxide is absorbing into the ocean and changing its pH level, so changing the acidity level of the ocean itself. And we've looked at how that can change the chemistry and availability of something like a carbonate ion. I don't want to get too far into the chemistry of it because I know we have quite a diverse audience with us. But it's really what it's doing is it's changing the availability of the carbonate ions, and that means it's harder for some marine life to build their structures and skeletons. So that's the big impact. If it is harder, then they have less energy for other things. They may be smaller, they may not be reproducing at the same rate. So the availability of tiny food for bigger animals is going down. So what we have, just to recap, is ocean acidification and its impact on humans and the 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 ocean up here. Really looking at sort of two things: is the those creatures with structures and skeletons from calcium carbonate, and then that knock-on effect on fisheries. So the next question we have is, which animals or ecosystems are most vulnerable to increasing acidity of the oceans? The Arctic is known as a sentinel system or an early warning system because ocean acidification is happening more rapidly here. So in terms of ecosystems, the polar regions were seeing increased or faster rates of ocean acidification than other parts of the world. But then, of course, we look at an ecosystem such as the coral reef that you may have near your schools. And coral is an animal that makes its structure, the amazing coral reef structure, out of calcium carbonate. So, of course, if there's less carbonate available, then those structures are going to be harder to build, or they might not be built as fast. And so that can have another impact on the reef, already suffering from a number of stresses from ocean warming to fishery impacts, dynamite fishing in some parts of the world, and also sewage and other types of runoff from nearby land. So which animals or ecosystems? Primarily those with with sort of calcium carbonate structures or shells, and the ecosystems, polar regions, and then the coral reef as well. Dominic would like to know, how will ocean acidification affect humans? We've sort of looked at that a little bit at the start of this Q&A, where we've been thinking about the impact on fisheries, and that's probably going to be the biggest impact. If we don't have a healthy ocean with healthy fish stocks, then we won't have that available to us, and especially to those 1 billion people. Sorry, I probably 1 trillion before, I'm getting mixed up with a number of other numbers here. 1 billion people who rely on fish for their primary source of protein. TNC Dandy, what is acid? It is essentially the measure of the number of available hydrogen ions in a solution. There we go. And it is important in terms of in the ocean, in terms of how that reacts with carbonate, and we see that forms bicarbonate. Bicarbonate, and so that is not then available to make shells and structures for. What's the biggest problem for the oceans? Plastic or climate or acidification or habitat loss? Wow. It's difficult to choose. I mean, I think that if you have to rank these things, what you'll find is that, I mean, probably a lot of people will say that ocean warming is probably the biggest single the oceans. But if, for instance, you have a coral reef that's affected by ocean warming, it has a greater chance of being resilient if it isn't also affected by other issues such as habitat loss, maybe of habitats that support the reef, such as mangrove and seagrass meadows, and if there isn't acidification, and if there isn't plastic smothering the reef as well. So we have a wrap up now. Which is the most urgent? What can you do to help the oceans? And I really think the first up is, if let's look at our carbon emissions, and let's also then second look at our plastic consumption, because those are two big oceans. First of all, carbon, and then plastics. I'm afraid that is all we have time for today. Do ask more questions or repeat those if you like Hannah's point of view on some of this, and it would be really wonderful to speak to you all. And until we have our next expert interview in an hour's time, it is goodbye from me and goodbye from Arctic Live. Bye bye.